1 2 1 2 1 2 1 2 1 2. Woo! So, back to this one, we are going to be looking at the optimization. So, how do we get the lowest common ancestor operation before the lowest common ancestor operation before without having to do this so many recursive calls and basically just identify the lowest common ancestor as earlier defined, right? So we call a function called lowest common ancestor what's it called or OOP, just a short stuff for optimized to separate it from what's it called the um the brute force. So now what do we go ahead to do? We call the current root, and then we call the lowest common ancestor, and we point it to none. Now we call help we call the helper function that takes in the current, right? And we could see that here current is the current, basically the root of the node, right? And then we call non-local. Now this is not like your everyday function, so I will just take some minutes out to explain what non-local does. Now non-local is a concept that tries to separate. So functions are like a space of their own. The right terminology is missing me right now, but it has uh will I say, because we have we have a global variable, and then we have the inner variable or the function variable. So now defining a LC, that's LCA here, would actually mean a totally different LCA from the one that is instantiated here, right? And the reason why we now call it non-local is because what we call it non-local, because we want to see, we are not looking at an LCA different from this guy. I wanted to say something funny there, but I'm going to hold myself. So it's a different LCA from the non-local, and it's not a different LCA from the non-local. It's the same. So basically, it's kind of a way of inheriting this LCA, and making sure that we make use of it within this function. So yeah, basically that's it in a nutshell. It's kind of inheriting a global variable and making use of it within your function without having to uh, redefine it and probably go around in like updating it differently. Now we say if current is none, we should return 0. Obviously, we've seen that to be a case where we get to the bare minimum or the bottom of the tree, and then we have the none, right? And then we say left count equals to helper current equals to left, and then current left count equals to helper dot left, right count equals to helper dot right, then self count equals to 0. And so basically, to explain just this block, right? So we are basically taking counts of our left and our right, and we are trying to build up a count for them, and you will now see how these counts are going to be subsequently used to identify the lowest common ancestor. So we also instantiate a self count and point it to 0, and we say if the current is equals to A, right, or current is equals to B. So basically, our current has already been defined as the root, right? So if any of them, if any of the current as its transverses has met any of the nodes we are looking for, that self count should increase to 1, right? And total is equal to the left count plus the right count plus the self count, right? And that's what our total is defined to be. And then we now say something, say if the total is equal to 2 and LC is none. Very, very, very vital block of code here. Very salient, but very vital. And we'll see what I mean by that subsequently. Now we say LCA is equals to current, right? So basically we are saying that we are now going to point this non-local global function to the current that we find, and we say return the total. And yeah, we return the total, and we go ahead to call the helper current and then return LCA, because we must have found our LCA at that point. Now, this also looks like somewhere where we would need, a conditional to also determine whether we return the LCA or not, depending on an error. But before I get into that, I'm going to try to take us through this function again, but using the a scalar draw to show us a graphical representation of what every block or every line of code is trying to do.